Hello students, welcome back to the classroom point. In our previous class, we have discussed the factors affecting the rate of reaction. That was the part 1. So in today's class, we are going to discuss the remaining factors that are going to affect the rate of reaction. So here the present class is mainly based on the catalyst and the activation energy and how this catalyst is going to change the rate of reaction, what other factors are influencing the rate of reaction as well. So let's begin the class now. Let us see the definition of the catalyst first. So here catalysts, basically the definition is, it is a chemical substance participate in the chemical reaction but do not consume in the reaction. Whatever the chemical substance we are taking in the chemical reaction. So catalyst is a chemical substance that participate in the chemical reaction but do not consume in the chemical reaction. Its chemical composition do not change, but only physical composition may change. It means if you take the solid catalyst, so that becomes either a powder form or in the form of the liquid state. So physical state of the catalyst may change, but its chemical composition do not change. What other things this catalyst is going to do is, it will not affect any thermodynamic functions. Thermodynamic functions are not changed by the catalyst. So what are the thermodynamic functions? Let us say example, delta G Gibbs energy, delta H change of enthalpy, delta S change of entropy. These thermodynamic functions are not changed by the catalyst. And second thing is, catalyst do not initiate the reaction. Do not initiate the reaction. It only helps to increase in the rate of reaction. Here, do not initiate the reaction in the sense, reactions are of two categories. They are spontaneous reactions and non-spontaneous reactions. So, non-spontaneous reactions are not affected by the catalyst. Only spontaneous reactions are affected by the catalyst. Because in the case of the spontaneous reactions, the reaction already begun. Now that reaction speed is increased by the presence of the catalyst. So that catalyst never initiate the reaction. If already reaction started, so that reaction speed can be increased by the presence of the catalyst. And we know that equilibrium reactions, both reactant and products are in the equilibrium state. So that reactant can be converted into the product side as well as product also can come back to the reactant state. So this constant, the rate constant for this reaction is called the equilibrium constant. Equilibrium position is not influenced by the presence of the catalyst. Catalyst only helps to achieve the equilibrium in a quick manner. That means the catalyst increase the rate of forward reaction and rate of backward reaction with equal quantity or equal measurement. So that it will increase the equal speed of the both forward reaction and backward reaction. That's why position of the equilibrium is not affected by the catalyst. Once position is not affected, automatically equilibrium constant is also not affected by the catalyst. What other things the catalyst is going to do is, catalyst increase the rate of reaction by decreasing the activation energy and by changing the path of the reaction. Changing the path of reaction. Now catalysts are of, we can consider two categories. They are positive catalysts and negative catalysts. Positive catalysts increase the rate of reaction by decreasing the activation energy of the reaction, whereas a negative catalyst decrease the rate of reaction by increasing the activation energy of the reaction. Now by seeing the activation energy profile diagram, then we can understand how this catalyst is going to influence the activation energy as well as the path of the reaction. Now let us see what is activation energy and its profile diagram, which is represented by EA, and a threshold energy, which is represented by ET. So if you take any chemical reaction, reactants basically converts into the products. But this process does not occur directly. Whatever this process is there, reactants directly will not be converted into the products. So initially reactants will be converted into the some activated complex. This is called the activated complex. Or it is also known as the transition state. This is highly unstable and cannot be isolated. So this transition state may convert into the product. Remember that the energy of this transition state is always higher than both reactants and the products. So that is the reason why to convert the reactant to the product, first of all we have to excite the reactant molecules. Why? Because if reactant molecules present in the reaction mixture, if they are converting directly into the products on their own, so that we don't get any reactant molecule, in every reaction we get only the products. And that products may be the again reactant molecules for the another reaction, so that only one direction reactions happens and we don't find at any given time reactants are unstable, so that reactants cannot be found. So but in the nature reactants are always available as well as products are also available. That means reactants cannot be converted directly into the product without providing the some amount of energy or to get activated. So that reactant molecules initially to get activated. Why activation is required? See, in the reactant molecules, there are bonds present between the atoms. So these bonds require some amount of energy. So these bonds are to be initially to be broken. So to break these bonds, two things are required. One is energy, we have to provide the energy. Second one is proper orientation and collision of the reactant molecules are required. So when these things are happening, then the breaking of the bonds happens, then formation of the new bonds takes place, that gives the products. That means initially whatever the reactant molecules are there, those reactant molecules by providing either some amount of energy or proper collisions or with orientation. So we need to take these reactant molecules to the higher energy state where the breaking of the bonds will be easy and that process becomes very easy. So that once this breaking of the bonds happens, the reactant molecules will be converted into the products. So taking the reactant molecules into the activated state, higher energy state is called the activation. Means reactant molecules get activated so that they can convert into the products. And whichever complex is formed in the middle state of the reaction, that is called the activated complex. Activated complex is always unstable. So let us take the profile diagram to understand this concept in an easy manner. So let us take this is the reaction coordinate. Reaction coordinate means how the reaction is proceeding. That is shown by the reaction coordinates that we are taking on the x-axis. And on the y-axis, let us take the energy. Imagine these are reactant molecules energy. So energy of the reactant molecules. So reactant molecules are to be converted into some products. So that initially reactant molecules are to be taken into the higher energy state. And finally this is the energy of the products. Reactant molecules energy is more than the energy of the products in this case. So energy of the reactants is more than the energy of the products. Even though energy of the reactants is more than the energy of the products, reactants directly not converting into the products because to break the bonds, the reactant molecules to get activated. So that we need to take these reactant molecules into the activation state so that the reactant molecules finally convert into the products. So this area is called the activation state or activated complex. It is also known as transition state. Now if you observe these energy profiles, energy of the reactants is here, energy of the products is here, and the energy difference between the both reactants and products in a particular chemical reaction is called the enthalpy of that reaction or else energy of the reaction. Now these reactant molecules are having, imagine 10 calories of energy they are processing, but to convert the reactant molecules directly into the products, these 10 calories are not sufficient, so that I need to take this reactant molecule to some higher energy state, which is called the activation state. And that energy is approximately, let us imagine 20 calories of energy minimum that reactant molecules to be possessed so that they can convert into the products. So the minimum energy that to be possessed by the reactant molecules to convert into the products is called the threshold energy. So this is called the threshold energy. Means once the reactant molecules, even though they are having the 10 calories, but they need minimum 20 calories to convert into the products. That means so that reactant molecules are to be get activated. So how much extra energy the reactant molecules must and should acquire from the environment or from the outside, that is extra 10 calories they have to absorb. So that energy is called the energy of activation. So in this energy of activation, reactants are converted into the products. In any given reaction, when reactants are converted into the products, that is called the forward reaction. So I am taking this one as the energy of activation for the forward reaction. So what is the definition of energy of activation for the forward reaction? The minimum energy that reactant molecules must acquire. Already they are having 10 calories. They need minimum 20 calories, extra 10 calories they have to acquire. So the minimum amount of energy that reactant molecules must acquire to reach the threshold energy called the activation energy, so that they get activated. Threshold energy definition is the minimum energy to be possessed by the reactant molecules. Actually they are possessing this much energy, but this is not sufficient. They must possess this much amount of energy. So the minimum energy that the reactant molecules to be possessed to convert into the products is called the threshold energy. So from this it is very clear that we can write down the threshold energy is equals to, this is the total 20 calories of energy. Already reactant molecules are having the 10 calories of energy. Energy of activation is remaining 10 calories of energy. So that threshold energy can be calculated as energy of the reactant molecules plus energy of activation. This is for forward reaction. So once in the absence of catalyst, the reaction is proceeding like this. This is the path of the reaction. But once you are using the catalyst is added. Catalyst duty is to change the path of the reaction so that it facilitates the fast of the reaction. It will take the reaction in a faster manner. That means reactants can be converted into the products in an easy manner like this. So imagine now in this case, when catalyst is used, this is in the presence of catalyst. In the presence of catalyst, this is the path. Energy profile diagram. This is in the absence of catalyst. So in the presence of catalyst, threshold energy is this much. Activation energy is only this much. So that this is the path of the reaction. So once you are using the catalyst, what it is changing is, it is changed the path of the reaction, it is changed the threshold energy, it is changed the activation energy, and once and the speed of the reaction also. See here, higher energy is required in this case to convert into the reactant molecules to the products. In this case, only less amount of energy is required for the reactant molecules to convert into the products. So in which case the reaction will be faster? Second case. That means reaction becomes very faster, means rate of reaction is increased by the catalyst by decreasing all these parameters. Once you are increasing the energy, for example, in another case, if energy profile diagram is like this, imagine this is the third case. Third case will be slower reaction, because once threshold energy increases, the energy acquired by the reactant molecules also increases. They need more energy to convert into the products. That's why once activation energy and threshold energy increases, rate of reaction decrease. Once activation energy and threshold energy values, see, threshold energy decrease and activation energy also decrease in the presence of the catalyst. Once these are decreased, rate of reaction value gradually increase. So catalyst is doing these things. It changes the path of the reaction, it changes the threshold energy, it changes the activation energy, and it changes the rate of reaction also. What it is not changing is energy of the reactant molecules not changed, energy of the products not changed, delta H value also not changed. See this, here in the presence of catalyst, in the absence of catalyst, both are meeting at the same area. So enthalpy of the reaction is not changed, and delta S value also do not change, delta H value also do not change. All thermodynamic parameters are unaffected by the presence of the catalyst. Now I want to convert this product into the reactant molecules. So when you want to convert the product into reactant molecules, look at this side, this much amount of energy is the activation energy. Activation energy for the backward reaction. Now in this particular case, which one is an easier process? Converting the reactants into products or products into reactants? Reactants into products, in both cases, in the absence of catalyst or presence of the catalyst, the activation energy is very less, so that the conversion becomes very easy. But in the case of the products to the reactant molecules, see that activation energy this much heavier is present, so that higher the activation energy means difficult to convert the product molecules into the reactant molecules. Now in this case, how to calculate this delta H value? Delta H value, enthalpy of the reaction, can be calculated by energy of activation for the forward reaction minus energy of activation for the backward reaction. Now let us see here condition. Energy of activation energy for the forward reaction is less than the backward reaction. So backward reaction value is more than the forward reaction value, so that the total value is equals to negative, delta H equals to negative. That is what we said, this is an exothermic reaction. Exothermic reaction. Energy is released. Second one is delta H. If backward reaction value is less and forward reaction value is more, then the value is equals to positive, so that is called the endothermic reaction. And third condition, energy of activation energy for the forward reaction is equals to the energy of activation energy for the backward reaction. This is not possible. Remember that always energy of activation energy for the forward reaction and backward reaction never be equal. That means every reaction must and should possess some amount of activation energy. If activation energy is not there, 100% of the reactant molecules will convert into the product, which is usually not possible. So that reactant molecules to convert into the product, some amount of energy is required. Let us see other profile diagrams also. If the diagram is given like this, reaction coordinate, energy of the reactant molecules, and this is the energy of the products, activation energy for the forward reaction, this is the activation energy for the backward reaction, this is the enthalpy change of the reaction, this is the threshold energy of the reaction. So for endothermic reaction, the profile diagram looks like this. Why? Because energy of the products is more than the energy of the reactants, energy of the products more than energy of the reactants, and delta H value is equals to positive. let us see, our diagram is given like this. A becomes A star. They had given the B, B star, and finally C. So here two activation energies are available for the forward reaction. You can see this is the energy of the reactants and this is the energy of the products difference, delta H of the reaction. This is the energy of activation, EA1. I am considering this one as EA1, and B is the intermediate. A star and B star are activated complexes. Or they are also known as the transition states. Transition states cannot be isolated, but intermediates can be isolated. They have some bond parameters also, but activated complexes do not have the proper bond parameter. They are only the higher energy states of their respective earlier compounds. So these are higher energy states. So these can be converted into the initially A converted to the A star, which is activated complex. This A star converted into the B, which is intermediate. This B again get activated to form the B star, and B star finally converting into the product. And here one more activation energy is there, EA2. So in these two cases, the question is about which is the slow reaction, which is the rate determining step. So I shall write down this reaction as A initially converted into the A star converted into the B, B converted into the B star converted into the C. In these two cases, A to A star, this much activation energy is required, and B to B star, this much activation energy is required. Higher the activation energy, slower the reaction. That means this is called the A to A star is called the rate determining step, and B to B star is called the fast step. So this is the rate determining step. This is the fast step of the reaction. Now let us discuss about the negative catalyst. Let us take a energy profile diagram for the negative catalyst. Imagine for the exothermic reaction, the reaction energy profile diagram is like this: energy of the reactants and energy of the products. So reaction going in this path, and this is the delta H value. This is in the absence of the catalyst. Let us imagine if you had the negative catalyst. So negative catalyst duty is to decrease the rate of reaction. How it can decrease the rate of reaction? A particular reaction rate can be decreased by increasing the activation energy. So that activation energy is increased. See, earlier activation energy is only this much, EA1. Now this much activation energy is there, which is EA2. So that in the presence of the negative catalyst, the rate of reaction gradually decreases by increasing the activation energy. Now let us see the collision theory also. So collision theory mainly focuses on the two things, that whenever the reactant molecules are taken, to convert the reactant molecules into the products, the reactant molecules must collide with each other. And during this process, collision theory considers that every reactant molecule is a hard sphere. So these reactant molecules, when come close to each other, they collide with each other, and afterwards only they convert into the products. So here all collisions do not lead to the formation of the products. There are two types of the collisions again here. Collisions which gives the products are called the effective collisions, which are not giving the products are called the ineffective collisions. So effective collisions meaning is only these collisions are converting the reactant molecules into the products, and remaining collisions do not give the products. So why effective collisions are giving the products? Why ineffective collisions are not giving the products? Effective collisions again mainly are having the two things. They are following the two things, that is orientation factor energy factor. energy factor already we discussed that. If the reactant molecules are having the sufficient amount of energy to convert into the products, that energy is called a threshold energy. So if the reactant molecules are having that minimum energy, then those collisions gives the products. What is the orientation factor? Orientation factor says that the reactant molecules must have the proper orientation. Otherwise, the collisions do not lead to the formation of the products. So let us take this orientation factor. I am converting the HI molecule into the products. So initially, the bonds will be broken between these molecules so that H and iodine bond. Here also iodine and H bond is going to break and new bonds are going to produce here. And if the reaction is proceeding like this, the previous bonds are broken and finally again you are getting the same molecule. HI and HI. You have taken the HI molecules, finally products are also HI molecules. Because these reactant molecules are not coming in the proper orientation. Now let us see what if the reactant molecules are coming in the proper orientation. If the reactant molecules are like this, old bonds will be weakened and new bonds are going to develop, and afterwards these old bonds are completely broken and giving the new bonds. So now H2 molecule and I2 molecule. In the earlier case, reactant molecules do not lead to the formation of the products, but in the second case, reactant molecules are giving the products. This is because in the second case, reactant molecules are in the proper alignment or orientation, so that collisions gives the products. In this case, those collisions are not giving the products. We can take one more reaction also. So methyl bromide when subjected with the aqueous alkali, this OH minus has the two chances to approach this carbocation. This OH minus has the two chances to approach this partially positive charged carbon. It may come from this direction or it may come from this direction. If it comes from this direction, the partial negative charge of the bromine will oppose this negative charge, so that OH minus cannot approach this carbon from the front side. So this is not the proper orientation. But OH minus can approach the carbon atom from the opposite side to the leaving group, so that OH minus approaches from this side. This is called the proper orientation, which gives the product as so the molecule is formed like this. So here, to develop the products from the reactant molecules, we need two things. Both is energy factor as well as orientation. See, if the reactant molecules are having both sufficient amount of energy and a proper orientation, in that condition only, those collisions leads to the formation of the product. Lack of any of these do not give the product. For example, in the case of the ineffective collisions, either they may have the sufficient threshold energy, sufficient amount of the energy, but they may be the lack of the orientation, so that they don't give the products. If they have the orientation but energy is not there, then also they don't give the products. So ineffective collisions are not having in both of these. Effective collisions are having the both of these. And here, in the case of the ineffective collisions, what happens if those two, any one of these is not present but collision is happened? When collision is happened, the reactant molecule just bounce back from their places and go to the other places, but no products are going to be formed. Only in the case of the effective collisions, the products are going to be formed. Now, let us see collision frequency. Collision frequency says that in a particular given volume, whatever the number of collisions happens, that collisions are called the collision frequency. In the given particular unit volume, if more collisions are happening and giving the products, they are called the collision frequency is higher. In a given particular volume, number of collisions are less, so that product formation also less, then collision frequency is less. From this, it is clear that when collision frequency increases, number of collisions increase. But all the number of collisions do not give the products. If they are having the proper energy and orientation, then when collision frequency increase, then product formation rate also increase. So these are all related by an equation. Rate equals to Z into e power minus EA by RT, where Z value says about the collision frequency. So once collision frequency increases and this value also increases, then rate of reaction value increases. So dear students, I hope you understand today's class. So we'll meet in the next class. Thank you one and all.